Welcome to lecture 38. The title of this lecture is the two-site Hubbard model. We're going to go through and analytically determine all of the energy levels of the Hubbard model on a two-site lattice where we have between 0 and 4 electrons in our system. So let me remind you what the Hubbard Hamiltonian is. The hopping term is minus t times the sum over spin of c dagger 1 sigma c2 sigma plus c dagger 2 sigma c1 sigma. You can see we counted the nearest neighbor pair 1, 2 once. There's only one nearest neighbor pair in the entire lattice because the lattice only consists of two sites. And so that is the hopping term. And then the interaction term is the sum I equals 1 to 2 of ni up, ni down multiplied by u. And you can see there are two terms there. It's n1 up, n1 down plus n2 up, n2 down. So it's a relatively simple Hamiltonian, but if we do the counting, there are n sites. In this case, n is equal to 2. So there are 4 to the n possible states because I could either have no electron, an up electron, a down electron, or an up-down electron on each site. And I have 4 for each lattice site that I have in the lattice, and so I get 4 to the n possible states. For the two-site Hubbard model, that would be 4 squared, which is 16. And so the matrix for this Hamiltonian is a 16 by 16 matrix. And in principle, I could just calculate all the matrix elements of a 16 by 16 matrix, put it on a computer, and diagonalize it. But here we want to use the symmetries to reduce the problem as much as possible to get it into a state where we can actually analytically determine all of the energy levels. Okay, so let's do some counting when I have little m electrons. Now, little m can run anywhere between 0 and 2 times n because I cannot have more than 2 electrons per site. Notice this counting is different than the way that I counted the total number of possible quantum states because the total number of quantum states does allow up to 4 different states per lattice site. But the total number of electrons I can have on a lattice site, I either have 0, 1, or 2 electrons on a lattice site. And so m will run between 0 and 2 times n, where big N is the number of lattice sites. So I just have to figure out how do I distribute those m electrons amongst the 2n different spin orbitals. So now I'm thinking about on each lattice site, I can either have no electron or an electron that is spin up, and I can have no electron or an electron that is spin down. And if I think in terms of the spin orbitals, and there are 2n spin orbitals, so the spin orbitals would be up for site 1, down for site 1, up for site 2, down for site 2 on the two-site lattice. And you can see there are 4 different spin orbitals. And I'm going to have to figure out how do I distribute the m electrons that I have amongst those 2n spin orbitals. And that's a simple combinatorial function, which is 2n choose m. And you can calculate that. That's 2n quantity factorial divided by m factorial divided by 2n minus m factorial. There are that many states that have m electrons. Okay, and I've already described to you precisely where that comes from. Let's do a check to make sure that that's really correct. So the way that we're going to check is we're going to sum the total number of electron states that we have. So we're going to sum m equals 0 up to 2n of this binomial factor 2n choose m. And now if you go and you look up the binomial theorem, you can see that that is given by the sum of those binomial coefficients. If I sum them from m equals 0 to 2n, that's just given by 2 raised to the 2n. And then if I recognize that 2 squared is equal to 4, you see that that's equal to 4 to the n. But we already determined that 4 to the n was the total number of electronic states that we have in the many-body problem. And so you can see that we are properly counting everything via this binomial theorem. So let's get concrete. We're going to work with big N equals 2, and that means I can have 0, 1, 2, 3, or 4 electrons on the site. Let's count the combinatorics. 4 choose 0 is equal to 1. 4 choose 1 is equal to 4. 4 choose 2 is equal to 6. 4 choose 3 is equal to 4, and 4 choose 4 is equal to 1. Those of you that are familiar with the Pascal triangle will recognize those numbers, 1, 4, 6, 4, 1, as the numbers that come up when I raise 1 plus x to the 4th power. Now let's add them all together. 1 plus 4 plus 6 plus 4 plus 1 is indeed equal to 16, and that indeed is equal to 4 squared, as we had mentioned at the beginning of the lecture. So we're now going to go through and calculate what those energy levels are for each one of those cases, and we're going to start now in the case where m equals 0. So I want to remind you that the Jz value was equal to 1/2 the quantity number of electrons minus number of lattice sites. So for us, that's equal to 1/2 little m minus big N over 2, which just becomes 1 because big N is equal to 2. So it is equal to 1/2 the number of electrons minus 1. So let's plug in m equals 0, and we find that mj is equal to minus 1. Now the only states that will allow me to have an mj equal to minus 1 are states that have total j equal to 1 or larger. So it cannot be a total j equals 0 state. It must be total j equals 1 or 2 or 3. But it turns out that the largest total j that I can have for any of these problems is equal to the total n divided by 2. And you can see that because the m equals 0 state is always the state that gives me the largest j value, and it always gives the smallest value of m sub j. And here the m sub j value is equal to minus 1. In general, it's equal to minus n over 2, where n is the number of lattice sites, and that tells me the biggest j I can have is equal to n over 2. So the biggest j I can have is 1. That means j is equal to 1. mj is equal to minus 1. I have no electrons, so the total spin is equal to 0. And that state is just the vacuum state that we just call the 0 state. And if I operate the Hamiltonian on it, because the Hamiltonian is in a normal ordered form, all of those C operators are going to annihilate against the vacuum, and so the energy is going to just equal 0. And of course that makes sense. If I have no particles, the energy should be 0. And we've now solved for the energies in the case where m is equal to 0. Let's now go on to a non-trivial case. Let's look at m equals 1. In this case, Jz is equal to 1/2 minus 1, which is minus 1/2. And that tells me that my total j must equal 1/2 because the j cannot be bigger than 1, and it must be larger than or equal to 1/2. And so the only choice is j equals 1/2. So I have j equals 1/2. I have mj equals minus 1/2. I have one electron. That electron has spin 1/2, so the total spin must equal 1/2 as well. Now we're going to consider the spatial symmetry. We're going to go back and take a look at this Hamiltonian matrix, and you can see if I interchange 1 with 2, the Hamiltonian does not change. So an interchange of 1 with 2 is a symmetry of the Hamiltonian. If you like, the Hamiltonian is even under an interchange of 1 with 2. And what that means is that I can organize my solutions in terms of odd functions and even functions under an interchange of the site label 1 and 2. So now let's come back to our m equals 1 state. We're now going to consider two states. We're not going to just consider the state 1 up and the state 2 up. We're instead going to consider the state 1, which is 1 up plus 2 up divided by square root of 2, and 1 up minus 2 up divided by square root of 2. And the reason why is those are the states that are even or odd under an interchange of 1 to 2. You can see the state 1 is an even function and the state 2 is an odd function. And because that interchange symmetry is a symmetry of the Hamiltonian, these two states cannot be coupled by the Hamiltonian. So they each should be eigenstates because there's only one of them. I just want to make sure that you're clear that the 1 up plus 2 up is a shorthand for 1 over square root of 2, C1 dagger up acting on the vacuum plus C2 dagger up acting on the vacuum. When you get used to working with these after a while, you start to recognize that you can really think of these as, sort of particles, as I was alluding to in the previous lecture, as sort of different colored checkers moving on a checkerboard or something like that. And so they almost take a life of their own. And so this shorthand 1 up plus 2 up is something that's very clear, and it should not be confusing at all when we use that notation, and I hope you will become used to it. Okay, when we calculate the Hamiltonian acting on that state, you can see that the hopping, let me actually pull up the state so we can carefully look at it. What the hopping does is it allows site 1, an electron in site 1 to hop to site 2 without changing its spin if site 2 is empty, and it allows an electron to hop from site 2 to site 1 if site 1 is empty, or at least if site 1 does not have an electron of the same spin on that site. So you can see the 1 up state can hop to 2 up. So if I apply the hopping operator to it, I'll get a minus little t multiplying the whole thing. The 1 up changes to 2 up, the 2 up changes to 1 up, and you see the state remains the same. And indeed, it is an eigenstate, and the eigenvalue is minus this little t. If I do the same thing with state 2, the 1 up goes to 2 up, the 2 up goes to 1 up, you see the state goes to minus itself, and so there's a minus sign that comes out, and the eigenvalue for that is going to be plus t. And each one of these is twofold degenerate because the upspin, I can do the exact same calculation for the downspin, and everything is exactly the same. Nothing changes. So the upspin is degenerate with the downspin. Of course, we know that because we know that the total spin is a good quantum number, and the ms equals minus 1/2 and ms equals plus 1/2 are part of the spin 1/2 multiplet. They must both have exactly the same energies. So we find in the end that we have two energies for the single electron case. They're degenerate. One energy is minus t, the other energy is plus t, and they're both twofold degenerate. Okay? I hope you can see that just by using these quantum numbers and rationally working through what are the possibilities, we find that we actually can find the eigenstates here without having to construct any matrices and without having to do any diagonalizations. And we're going to try and move and push that idea even further as we go into the situation where we have two electrons. Now for the two electron case, we have some j equals 1 states. Those are going to have mj equals 0 because again the mj value is 1/2 m minus 1. M is equal to 2, so that becomes 1 minus 1, which is equal to 0. The state that has j equals 1 is always constructed out of pairs of electrons on different lattice sites. Every time I have a pair of electrons on a lattice site, the total spin of that state is equal to 0. Another way of saying it is that I can think of the state with mj equals minus 1 as the j plus operator acting on the state that had mj equals minus 1. And when I apply that raising or lowering operator, what we find is the raising or lowering operator, since the j commutes with the s, it does not change the s value. So because the state that had m equals 0, no electrons, had total spin s equals 0, when I apply a j plus on it, that state continues to have s equals 0. So we learn the j equals 1 state, when I raise it by adding a pair, will have mj equals 0 and will continue to have s equals 0. So the state is given by j plus acting on 0. We can write down what that state is. It's 1 over square root of 2, 1 up, 1 down, minus 2 up, 2 down. We're going to call that state state 1. If I act the hopping operator on that, I'm going to get a minus t pulled out in front. The 1 up can hop to a 2 up. The 1 down can hop to a 2 down. The 2 up can hop to a 1 up. The 2 down can hop to a 1 down. We have to add all of those together. I am not interchanging the order into some standard form, but I'm instead writing it as 2 up, 1 down plus 1 up, 2 down minus 1 up, 2 down minus 2 up, 1 down. I'm doing that on purpose, not because I do not want in general to put things back into some standardized form, but simply because at this stage we can work with them in that form, keeping in mind that the ordering is important. If I interchange the order of the two electrons in the label, that will produce a minus sign. So now you can see that when we do this expansion, the two terms come in with opposite signs and they cancel each other, and the hopping matrix acting on this state is equal to 0. When we look at the U operator acting on this state, we just have to count the double occupancies in the state, and you can see 1 up, 1 down, that has 1 double occupancy. 2 up, 2 down, that has 1 double occupancy. So the whole state has 1 double occupancy. And so U operator acting on this state is going to give me the number U acting on this state. And so the energy is equal to U. Of course, again, we already knew that because we knew that J plus raises the energy by U. So it took the energy of the state that had m equals 0 and raised it by U, and I immediately know that the energy is equal to U. Okay? Nevertheless, I went through this very carefully and pedantically to make sure you could follow and understand how we got that particular eigenstate and how that construction worked. Okay, so we worked out the J equals 1 cases. What's left are J equals 0 states. Now, when I have two electrons, I'm combining a spin 1/2 with a spin 1/2, and I can get an S equals 1 state, and I can get an S equals 0 state. So we're going to start by looking at the S equals 1 states. We're going to remember that the S equals 1 states are all degenerate in energy. So I'm going to work with the simplest state to do a calculation on, which is the fully polarized state. The only way I can get a fully polarized state with S equals 1 is to put an up electron on site 1 and an up electron on site 2. I'm going to call that state state 1. Now, I cannot move that electron because I cannot hop from site 1 to site 2 because site 2 already has an occupied electron of up spin. And so the hopping operator acting on that state is going to annihilate that state. There are no double occupancies on that state, so the U operator is going to annihilate that state. So when the Hamiltonian acts on that state, it gives 0. So the energy is equal to 0. And that's an energy that is threefold degenerate because it's degenerate with the ms equals +1, which is the case we looked at here, the ms equals 0, and the ms equals -1 states. They're all degenerate. All right, so what we're left with then is a J equals 0 state and MJ equals 0 state, and that state also has S equals 0 because we just looked at the S equals 1 state. So for S equals 0, it turns out there are two different ways that I can get an S equals 0 state. I can look at the state that is perpendicular to the doubly occupied state that was constructed with a J plus acting on the vacuum. It's easy by sight to see that that state is 1 over square root of 2, 1 up, 1 down, plus 2 up, 2 down. And then I can look at the state that is perpendicular to the S equals 1 state when ms is equal to 0. So if I hit that 1 up, 2 up state with a S minus operator, it would equal 1 up, 2 down, plus 1 down, 2 up. And the state that is perpendicular to that is obviously 1 up, 2 down, minus 1 down, 2 up. Or you might just have remembered that the singlet state is the combination of up, down, minus down, up. And so that state I'm going to call state 2. So we have two states that have J equals 0, MJ equals 0, and S equals 0. There are no multiplicities due to spin because the total spin is equal to 0 for these two states. Let's act H on the first state. You see it's going to take the 1 up. It multiplies the whole thing by minus t. It's going to take the 1 up to a 2 up. It's going to take the 1 down to a 2 down. It's going to take the 2 up to a 1 up. And it's going to take the 2 down to a 1 down. You see I can combine two of those two terms together because I have a 1 up, 2 down twice, and I have a 2 up, 1 down twice. So a factor of 2 comes out. And you see that hopping term is going to minus 2t times state 2. Now if I act the U operator on this, you see that that has one double occupancy. So it just gives U times that state. So H acting on state 1 gives minus 2t times state 2 plus U times state 1. We're going to do the same thing with H acting on state 2. We can immediately see that that state has no double occupancies, so the U operator is going to give 0 when it acts on it. Let's do the hopping term. The 1 up goes to 2 up, the 2 down goes to 1 down, minus the 1 down goes to 2 down, and the 2 up goes to 1 up. Here we have to be very careful. It looks like we can cancel 2 up, 2 down, minus 2 down, 2 up, but we cannot. We have to interchange the order of those two because they're really representing those fermionic creation or annihilation operators. If I interchange the order of those two, you see that the sign has to change because I'm moving one creation operator past another creation operator, but they're fermionic operators and they anti-commute. And the same thing is true about the 1 down, 1 up, and you can see that again it gives me twice the value, and it gives me a minus 2t times the state 1. So now we can construct the matrix. I'm going to take that vector h with 1 acting on it. I'm going to multiply it from the left with state 1. That's the 1, 1 matrix element. And you can see the 1, 1 matrix element is equal to u. I multiply it with a bra that is state 2 from the left, and I get the 2, 1 element when I do that, and that is equal to minus 2t. I take the h acting on state 2, I multiply it by a 1 bra, and I get the 1, 2 element, and that's equal to minus 2t. And then finally, I multiply it by the state 2 bra, and I get the 2, 2 element, and you can see that state is equal to 0. So we get this 2 by 2 matrix to determine the energy eigenvalues in the j equals 0, s equals 0 sector. It's easy to find what the characteristic equation for that is. Just subtract E times the identity, take the determinant. You should do this calculation. You will find E squared minus UE minus 4t squared is equal to 0. I can easily solve that quadratic equation, and I get that the energy is equal to U over 2 plus or minus 1/2 the square root of U squared plus 16t squared. Okay, now that's all of the states for m equals 2. We're going to go and take a look at a summary of that. I'm sorry, we're doing a summary now for all of the states equal to or less than half of filling. We have the m equals 0 state, j equals 1, s equals 0. That state had e equals 0, it was one state. We have the m equals 1, j equals 1/2, s equals 1/2, e equals plus or minus t. That was twofold degenerate, and so there are 4 states because they're 2 different energies times twofold degeneracy. For m equals 2, we had j equals 1, s equals 0. That energy was equal to u. There was one state. We had j equals 0, s equals 1. That energy was equal to 0. There were 3 states due to the SU2 multiplet because it was a triplet. And then we have j equals 0, s equals 0. There are 2 states there, and the energies were u over 2 plus or minus 1/2 square root of u squared plus 16t squared. You can see that the ground state always has minimal pseudospin because the ground state for m equals 2 is the u over 2 minus 1/2 the square root of u squared plus 16t squared, because that is a energy value that is always less than 0 as long as the u is bigger than 0. And similarly, if we look at the negative u case, what we find is the lowest energy is going to also be, let's see, the lowest energy state is going to be j equals 0, s equals 0. That's also going to be the lowest energy state. In general, we have minimal s for u less than 0 and minimal j for u larger than 0. Okay, let's now look at the ground state wave function for m equals 2. So I have to go back and plug into that equation. We plug in what the energy eigenvalue is. We're thinking about u greater than 0. So we're looking at the energy is u over 2 minus 1/2 the square root of u squared plus 16t squared. We plug in that energy eigenvalue. We solve for the alpha and the beta. There's a little bit of algebra that one has to do. You can see we're going to just look at the top line. I'm going to get this complicated expression, u over 2 plus 1/2 the square root times alpha minus 2t times beta. That whole thing equals 0. That gives me a relationship between beta and alpha. I also use the fact that alpha squared plus beta squared equals 1 because I'm working with a normalized state. That allows me to substitute in for the beta using this relation. And so I get alpha squared times this complicated expression is equal to 1. We got to go through some algebra. So I get 1 plus the square of this. I get a u squared over 16t squared. I get a plus 2u over 16t squared times the square root. And then I get plus 1 over 16t squared times u squared plus 16t squared, which is going to give me u squared over 16t squared plus 1. I can combine some of the terms together, and I'm going to get alpha is 1 over the square root of 2 times 1 plus u over 16t squared times the square root, plus u squared over 16t squared. And then using the relationship to the beta, we find the beta is equal to the square root of 2t times u over 4t plus 1 over 4t square root of u squared plus 16t squared, square root of that whole thing divided by u squared plus 16t squared to the 1/4 power. What we did was we can convert that alpha expression by recognizing that that object in the parenthesis can be factorized. I can factor out a square root of u squared plus 16t squared divided by 16t squared times u plus the square root of u squared plus 16t squared. I'll let you carefully work that out, but you see if you take that square root of u squared plus 16t squared, you multiply it by the u, I get u times that square root. That's the middle term in the parentheses, and when I take the square root and multiply it by the square root, I'm going to just get u squared plus 16t squared, and those are the other two terms. So think about it carefully. The key point is that 1 plus u squared over 16t squared can be written as 16t squared plus u squared divided by 16t squared, and that's actually equal to that square root quantity squared divided by 16t squared. So I can factor out the square root divided by 16t squared from both terms. Okay, that just provides a simplification, and of course I use that simplification in determining what the beta value is. So now psi is equal to alpha times the state 1 plus beta times the state 2. Let's look at some limits. When u goes to 0, if I take that limit, you see the only term that's going to survive are the 16t squared terms. And we actually find when all the dust settles that alpha is equal to 1 over the square root of 2 and beta is equal to 1 over the square root of 2. So we can plug that in using the expressions for 1 and 2, and you see it's equal to 1 up, 1 down, plus 2 up times 2 down, plus 1 up times 2 down, minus 1 down times 2 up. And it turns out that this can actually be factorized. It's 1 over square root of 2, 1 up plus 2 up times 1 over square root of 2, 1 down plus 2 down. You see, if you multiply that together, you get 1 up, 1 down, plus 1 up, 2 down, plus 2 up, 1 down, plus 2 up, 2 down. And so you can see that that thing properly factorizes into product of two wave functions. And this is the bathtub principle. It says fill in the two lowest single particle energy states. If you go back and you look at the solution for m equals 1, the lowest energy state, the one that had an energy of minus t, was the state that was 1 up plus 2 up. And you see what we're doing here is we're just filling in those two lowest energy states. And so the wave function is just a product state of those two states. And that's what we get when u is equal to 0. On the other hand, if we look at u goes to plus infinity, we're going to find alpha goes to 0 because you see it's got a u in the denominator and there's no u in the numerator. That means beta is going to go to 1. So that means the state psi is going to go to state 2, which is 1 over square root of 2, 1 up, 2 down, minus 1 down, 2 up. You can see that that state has no double occupancy. Again, this is exactly what we expect to have happen. When u is equal to infinity, if I have a double occupancy, would cost me an energy equal to u, which is equal to infinity. So I have to project onto the states that have no double occupancy, and that state turns out to be the ground state. In the other case, when I look at u goes to minus infinity, there's actually a cancellation in the expression for alpha. It's better to work with the first expression rather than the second expression for alpha. There's actually a cancellation there, and you find alpha goes to 1 and beta goes to 0. And that means psi goes to the state 1, and it's equal to 1 over square root of 2, 1 up, 1 down, plus 2 up, 2 down. And of course, that state makes lots of sense too, because if u is very, very large and negative, I want to form double occupancies, and so I'm going to have a sum of the two double occupancies that I can form. The parity tells me it's either going to be an even sum or an odd sum, and it turns out this even sum is the state that has the lowest energy, so I get 1 up, 1 down, plus 2 up, 2 down. Okay, so as I mentioned before, when u is equal to 0, we fill the lowest states of the band structure. This is the bathtub principle, and you get that state. When u is equal to infinity, there's no double occupancy. It also tells us that the energy is going to go to 0 in that case. But we find that also the state 1 over square root of 2, 1 up, 2 down, plus 1 down, 2 up, and the state 1 up, 2 down, and the state 1 down, 2 up, they're all degenerate, and they all have energy E equals 0. So that becomes a degenerate perturbation theory to determine what is the energy of the state and which state wins when u is not exactly infinity but is very, very large. And one would have to do degenerate perturbation theory to figure out what that lowest energy state is. Of course, since we have the exact solution, we know it's the state that is in the j equals 0, s equals 0 sector. So the s equals 0 state is the lowest in the limit as u goes to infinity. Again, as u goes to minus infinity, we have only doubly occupied states, and the state 1 up, 1 down, plus 2 up, 2 down is degenerate with 1 up, 1 down, minus 2 up, 2 down. Both have an energy E equals u, but if u is not exactly equal to minus infinity, then the state with the plus sign will be lower in energy than the state with the minus sign. All right, so we're going to now summarize for the general case. What we find is when u is equal to infinity at half filling, All singly occupied states are degenerate. The system is frozen in an insulator, as we had described earlier when we were talking about the Hubbard model. But as U becomes less than infinity but large on a bipartite lattice, the S equals 0 state is the lowest in energy. And if we make the U smaller and smaller, eventually that insulating state gets broken and it becomes metallic. Now, if we perform a partial particle-hole transformation, that will convert S to J, and so the ground state for U equals minus infinity has all doubly occupied states degenerate, but for U greater than minus infinity but large and negative, the state with J equals 0 is the ground state, and we get that from the partial particle-hole transformation. Then in the article that is one of the readings for this lecture, you can learn about other approximations to the Hubbard model. They're called different kinds of Hartree-Fock approximations, are talked about in that paper, and they compare those approximations to the exact solution to see how accurate they are for different U values. That's kind of viewed a little bit as old-fashioned at this stage, so we're not going to really examine that further here, because there are more sophisticated techniques we can use to at least give us better approximate answers to what the behavior of the Hubbard model is. So that's going to conclude this lecture. That's the end of lecture 38. We have 2 lectures left. The next lecture we're going to talk about magnetism in the Hubbard model, and we're going to prove a very interesting proof that shows a situation where the Hubbard model has ferromagnetic solutions as the solutions always. And then in the last lecture we're going to look at this question about the spin eigenvalue of the ground state when the interaction is repulsive on a bipartite lattice.